Hello, welcome back for the video for lesson 4.3. So in lesson 4.1, we learned about one-to-one functions and inverse functions. And then in 4.2, we introduced exponential functions. And so it's only appropriate that we look at or contemplate, think about what could be the inverse function of an exponential function. And that is a logarithmic function. Okay, so the definition of a logarithmic function says if we let a has to be greater than 0, it cannot equal 1. If x is greater than 0, then the logarithm of x with respect to base a is denoted by y equals log base a of x. And so when we say base a, it's going to be the same base in the exponential function too. So that's nice. That's why we say base a here and base a here. So the number a is known as the base, thus the functions, function of x equals a to the x, and the g of x function log base a of x are inverses of each other. So we can translate in between them. So let's do that. Example 1, we're going to translate from the logarithmic statement to the exponential statement. So log base 3 of 27 is equal to 3, which means that this 3 is the base, and then this 3 is the exponent. Equals to 27. So likewise, log base 4 of 1/4 is equal to -1. This 4 is the base. This 1/4 is the equal to, and this -1 is the exponent. Let's go the other direction. So example 2 says, let's say we have exponential form and we want to write it in logarithmic. So this is the base in the exponent. The base in the exponent is the base in the logarithm. So it's log base 4, and then of this 4 equals that should say 64. That's a typo. That should say 64. Log base 4 of 64 is 3, because 4 to the third is 4 squared is 16 times 4 is 64. That should say 64. On your notes, it'll say 64. Likewise, this says 10 to the 1/2. So that 10 is my base. So it's log base 10 of the square root of 10 is 1/2. Because 10 to the 1/2 is the square root of 10. So we're going to practice going back and forth with them. So let's look at example 3 when we have a missing piece. Because when you have a missing piece, then you're forced to think about it in the respect of a logarithm or exponent. So this says 5 to the power of 3 is what number x? And that is 125. So this means that log base 5 of 125 is 3. Okay. Some things that we know about logarithms. A common logarithm is what it's called when it's base 10. And a natural logarithm, they're going to use that as ln, is when we have base e. And remember, we learned about that natural number e back in unit 4.2 in the last lesson. Okay, so example 4 says without using a calculator, evaluate the following expressions. So log base 10 of what is 2/3? It's what they're asking. So this means if I take 10 squared, that's 100. And then I'm going to take the cubed root of 100. So this is the same as saying x is equal to 10 to the 2/3, or the cubed root of 100. Because 10 to the 2/3 is a cubed root of 100, which is not an even root. Let's look at natural log of e of 4/3. Natural log of e, they actually cancel each other out because y equals the natural log of x is the inverse function of e to the y. So it's like multiplying and dividing cancel each other out. So that is just 4/3. Okay, and that's because natural log is base e. So you're basically saying if it's base e, natural log is base e. So then you're saying e to the what x will give me e to the 4/3. Well, then I know that my x just has to be 4/3. The change of base formula is a way to calculate logarithms without a calculator if you needed to, or look at them in a different way to make things simpler. But now with calculators being so efficient and Desmos, you really don't need the change of base formula, because you can now just put it in the symbolics in Desmos. So I'm going to show you that here in a minute. So the change of base formula says when I have log base a of x, I can just put them both in log base 10. So it'll just be log base 10 of x divided by the log base 10 of a. Is how you would find that. So for instance, if I wanted to find the log base 6 of 15, I would just do log base 10 of 15 divided by log base 10 of 6. And I'm going to show you that they come up with the same answer in Desmos. Okay, so right here, log base, and when there's no base, that it's assuming it's base 10. So log base 10 of 15 divided by log base 10 of 6 is 1.51139. And then if you use the log base formula in Desmos, it's log of 6 of 15. And you can just type log. Oops. You have to go to the functions menu down at the bottom and scroll down. And it's under the calculus. And if you choose log little a, it'll let you do that. So you can do log base 6 and then go and put in parentheses your 15. So you can see if you look at just the log, this is the log base 5 of x. But if you look at just the log base 10 of x, it is the same as y equals 10 to the x. And remember, they are going to be symmetric around the equation of y equals x is what we learned back in lesson 4.1. So just kind of getting used to the graph. Let's go back to our paper notes so we can see the graph here of what they look like. Put D here. Just some basic graphs. You have log base A when A is greater than 1, and then log base A when A is between 0 and 1. So just like in exponentials, right, we could have our growth factor, which is the A, that multiplier can be bigger than 1. That's a growth. And when that base A is between 0 and 1, it's a decay. And that's what it looks like here in the logarithmic form. And here it gives you the vertical asymptotes on both. They have a vertical asymptote at x equals 0. And then when A is greater than 1, it's an increasing function. And when A is between 0 and 1, it's a decreasing function. So some good info about the graphs right here. So example 6 says for the function f of x equal to a negative log x, find the domain, sketch a graph, and find its range. So a negative log x. So in this case, that means it's a negative of log base A of x, where A must be 1 in this case because A must be 10 because it's just when it's a basic log, we always assume it's 10. So A is 10, which is greater than 1. But it's negative out in front. So that is going to look like, let's go ahead and just put this here. So it's going to be a decreasing function. The one application that is used with logarithms that we're going to do a little project, you're going to find that assignment in Canvas, but it's around the Richter scale. So the Richter scale is a scale that's used to equate the intensities of earthquakes so that you can compare the size of different earthquakes to each other. So it says, since the intensities of earthquakes vary widely, they are measured on a logarithmic scale known as the Richter scale. And we use this formula here. We take the log of I over I0, where I represents the actual intensity of the earthquake and I0 is a baseline intensity used for comparison. The Richter scale gives the magnitude of the earthquake. So it says, find the intensity in terms of I0 of a quake which measures 7.2. Let's look at that. So since we know that this earthquake measured 7.2 on the Richter scale, we can write it as 7.2 equals the log of the intensity with respect to the base intensity. And so this is our common log of 10. So that means we can really say that this is 10 to the 7.2 is equal to that ratio. And so I is going to be 10 to the 7.2. And so we're going to look at what is 10 to the 7.2 is 15,848,931 5.92. It is 15 million times bigger than the base earthquake. So it's pretty strong. That's 15,848,930, almost 2 times bigger. Okay. Logarithms can also be put in terms, distance can also be put in terms of logarithm. So it says Saturn is 9.3 times 10 to the 8th miles from the sun. Find the common logarithm of this distance. And so 9.3 times 10 to the 8th is log base 10 of this number. Of 9.3 times 10 to the 8th. So this is going to be, I'm just going to use one of these. And then it's going to be 9.3 times 10 to the 8. So that is 8.968. Is the common logarithmic distance from the sun. So when they compare them to each other. Let me show you that on my paper then. So we mainly learned in this lesson what the graph should look like and the change of base formula and how to translate from exponential to logarithmic form. So catch me back for lesson 4.4. We're going to look at the properties of logarithms.